In this screencast, I want to show you the multipole expansion and how it relates to the dipole potential that we were talking about in the last screencast. So in the last screencast, we talked about what a dipole is, why we're interested in them, and then I just gave you the potential for a dipole. Here I want to show you where that potential comes from. It's just a mathematical expansion. It's actually not terribly difficult, but it's worth looking at. We can also look at other terms that you may talk about in more advanced E&M classes, which would be quadrupoles and octupoles. But first, how do we get the potential for a dipole? Let's again talk a little bit about our motivation here. We're looking at a point very, very far away. In this case, we're looking at a point far away from a charge distribution. And in the end, what I really want is the electric field at point P. I'm always interested in the electric field at point P, but we're going to get it through potential because we've just learned that the potential is much easier to get typically than the E field. We can look, this is our formula for potential. There's no vectors here. We don't have to worry about transforming spherical components, spherical unit vectors into Cartesian components. All we need to worry about is what this R script is. All right, again, and if we're looking at a distribution really, really far away, if there is some net charge on this distribution, a distribution far away, very far away, always looks like a point charge. But we're going to look at something where the total Q on this thing is zero. The positive and negative charges are spread out in a way that actually gives field. And if we look far away, we're not going to just say that the E field is zero and the potential is zero. Because of the distribution of maybe there's more positive charge up here, negative charges up here, we actually get some net field at P. And this is the question we're interested in. So if the whole charge distribution is zero, what are the fields at P? All right. We'll pretend this has some charge, though, just to begin with, and you can see how the monopole term, as it's called, will dominate. And if the monopole term vanishes, then the dipole term dominates. All right, so what we have set up over here is a charge distribution. The vector from the origin to the little volume element of charge that I want to integrate is r prime, and the vector from the origin to the point of interest is r. When we take our limit here, we're going to make an approximation. We're going to be interested when r is much, much bigger than r prime, but we're not going to go there just yet. The distance between the element I'm interested in and the point is going to be r script vector, and the magnitude of r script vector by the law of cosines is this quantity down here. Griffiths uses the angle alpha between them. I like that, actually. That keeps it general. We might change this to theta prime if we coincide our r prime along the z-axis, but let's put this element of volume just out generically here, and then the angle between it is alpha. All right, let's write the magnitude r script in a little different way. So r script is equal to, I'm going to pull out an r. So that's like taking an r squared out from inside the parentheses here. So that'll leave 1 plus r prime over r squared minus r prime over r, times 2 cos alpha all to the 1/2. And then we're going to rewrite it like this. R 1 plus epsilon to the 1/2. And you can probably see where this is going. We're going to look at what happens when epsilon is very, very small, and then we can take a binomial expansion. So epsilon is just equal to r prime over r squared plus 2 times r prime over r cos alpha. Okay, so epsilon is much, much less than 1 when r is much, much greater than r prime. And that's what we're interested in. We're interested when our point r, which is our point of interest where we want to calculate the electric field eventually, is much, much, much farther than points on the charge distribution. Okay, remember r is from the origin to the charge distribution, and r is from the origin to our point of interest. And so this basically says we're looking really, really far away, and when we're looking really, really far away, epsilon is small. So we can rewrite 1 over our script that's in our integral of potential. That's just going to be equal to 1 over r, 1 plus epsilon to the minus 1/2. And we can basically binomially expand that. That's going to be equal to 1 over r, and here comes the expansion. It's going to be 1 minus 1/2 epsilon plus 3/8 epsilon squared minus 5/16 epsilon cubed, and so on. So plugging the 1 over r into our equation for potential, we get the following down here. All right, the 1 over r comes out, and the charge density stays in, and then we have this binomial expansion. Again, this is just plugging it into the format for what we know the potential of a generic charge distribution. All right, so the charge density stays in, and this basically represents this, and the 1 over r gets factored out, is that 1 over r script that we had on the previous screen, integrated over the volume. I'm not going to do all the derivation that Griffiths does. You can find this on page 153 if you want to look at all the detail, equation 3.93 on down. But when we plug in that epsilon from the screen before, what we get is the expression down here. And let me highlight some of this. You might notice already that this looks familiar. This term here should look familiar to you. All right, that's just Q. All right, and so the entire term, including this Q, the 1 over r out front, and the 1 over 4 pi e naught, we write as the monopole. All right, this term dominates when the total Q, when this is a non-zero quantity, these terms that we're going to talk about next are negligible. This one goes like 1 over r squared, this one goes like 1 over r cubed, and remember, really far away, so r is really, really big compared to r prime. The next term over here, this might look familiar if you were paying attention in the previous screencast. This term over here is the dipole term, and this is related to the dipole moment. I'm just going to write dipole. The dipole moment is a vector quantity. This isn't a vector here because this is the potential, and I'll write it on the next screen, how we can rewrite this expression in terms of the vector dipole moment. The quantity down here now, this integral, is going to be related to the quadrupole moment. Quadrupole. All right, and if you have no idea what a quadrupole is, you can think of it as a sum of a configuration of 4 charges, or actually 2 dipoles. So remember, the dipole was a positive and a negative charge, and we thought of them like little arrows. So the dipole moment is these little vector arrows. This is this is 2 dipoles now, and the quadrupole, again, we can recast this, and this isn't the quadrupole moment isn't a vector quantity now. It is a tensor. But in this format here, because this is a scalar potential, the quadrupole, even though the quadrupole moment itself is a tensor, this piece of it is a scalar. And even the dipole is a vector. This piece of it, written as potential in the format of potential, is a scalar as well as this. All right. Once again, if we're looking very, very far away, and we have some net charge Q. Remember, this is just the sum of the charge density over the volume. That's going to be Q total. If Q total exists, this is way bigger than the term here and the term here and any other further terms. The next one will be the octupole. So the monopole dominates if there's net charge. If there's no net charge, though, then the dipole dominates. And this is our case, as it will be for dielectrics, when we have this neutrally charged glass sphere, whatever shape it is, or plastic, the net charge is 0, so the monopole term is gone, and then we have to think about the contributions from the dipole potential. I'm going to rewrite this in a little differently on the next screen so you can see how it connects to the previous screencast, and then we'll move on to fields and dielectrics connecting these previous 2 screencasts, and some sample problems in class, and maybe some sample screencast problems as well. So here's the potential, at least up to the quadrupole term, and it's all its compact glory. Again, here's the monopole term. It goes like 1 over r. It dominates, and so you don't really worry about any other terms unless the total Q is 0. Here is the dipole contribution. It goes like 1 over r squared, and here's the quadrupole contribution. It goes like 1 over r cubed. This we've done a lot, or we've talked about quite a bit. Q is just going to be the charge density summed up over the volume of the charge distribution. The dipole moment we just started briefly talking about in the screencast, and this these are our little arrows here, and it is the integral over the charge distribution, but times the vector to the place you're integrating, the r prime. And the quadrupole, this is a tensor quantity. These are matrices, actually. This is a unitary matrix, and this is a 3x3 matrix as well. We won't be doing the tensor quantities. We can save that. You can save that for graduate school or independent study, or even more upper level advanced, but it's there, and we can do this. It's not terribly hard. It's just tedious and nasty. The next term that's missing here is the octupole, and so on and so on. And again, this is like 2 dipoles acting together, or 4 charges, 2 charges, 1 little dipole arrow, and this scalar quantity is just the sum of the charges.